Hello, everyone. My name is Matt Barami from Wolfram Research. Welcome to the third session of live streaming events with Dr. Alan Calvitti. I would like to add that Alan has a PhD in electrical engineering and computer science from Case Western Reserve University. He's also currently a data scientist at Bank of America working on the mobile app development. Also, Alan has a book on data science, which is under publication by Wolfram Media. Today, Alan will discuss about the unique symbolic feature of Wolfram language, some examples from his book, and also FICO challenge that he discussed in the previous session. If you missed Alan's previous lectures, you can watch it on Wolfram YouTube channel. Alan has also a post on Wolfram community, and you can reach out to Alan directly if you have any question. Without further ado, let us welcome our instructor, Alan Calvitti.
Thank you, Matt, and glad to have you back, everyone who's joining. This is the third coding session that is associated with my book that we're going to publish on Wolfram Media called Functional Dataflow. In this particular session, I'm going to go through a couple of small bullet points and then get back into the FICO Explainable Machine Challenge entry that I put together that I discussed in the previous two sessions. So obviously, I'm not going to start from the very beginning, but I'll just conclude the session because we're about one half or two-thirds of the way into it. Okay, I'd like to start the session though by proposing sort of like a bigger picture that we want to create these courses and sort of material that kind of is a bit larger than just like a single shot sort of teaching moment. So I'm going to start just by some motivation here before we get into the technical aspect of here. I just read this article in the Wall Street Journal. I think that's important for people to understand what data science and the different components of the data science. They include mathematics. You have to know a lot of math and statistics and linear algebra and graph theory and so on. And you have to combine that with a lot of computer skills, coding skills, let's say, and chops. And then you also have to have some sense of the business propositions in data. So I thought that this was a really interesting article today. It discussed it was a vice president of analytics and cloud compute at IBM, who basically said that data challenges are halting IBM projects. And you can read it. It's a very short article. It's online, where I'll be happy to share it. But I thought this quote was very informative. He's basically saying that Mr. Krishna is saying that as you run out of patience along the way, because you spend your first year collecting and cleansing the data, and then you say, wait a moment, where is the AI? I'm not getting the benefit. And you kind of bail on it. In other words, people put in so much effort just focusing on the end goals, and they start from these very heavy-duty algorithms or machine learning and TensorFlow and all these things. But there's a lot of prep work that has to be done before that, because it's essential that the data be there and be there in a way that can be used by the machine learning algorithms. So I think this is a very important lesson. We certainly see it in my current job. I've seen it in every single project that I've been on, where the data wrangling components, as they're called, meaning that you have to get the data in shape, structured, and in a way that the machine, that any other subsequent algorithms or statistics can be used, is actually the bulk of the problem and is the bulk of the work that has to be done. So I hope that everybody can sort of like understand this is a major challenge for compute going forward. So I'm not going to spend too much other time on that, but if there are any questions about this, we'll be happy to discuss. Okay, so the main point that I want to discuss now is symbolics. So when people talk about symbolic-oriented programming, let's just say, I'm just calling this like symbolics, but in computer science and in programming languages, typically people distinguish between various aspects of programming languages, such as object-oriented versus procedural versus functional languages. And very rarely do people stop and discuss symbolic-oriented languages. And I think that that's a shame, because the Wolfram language actually is quite unique. And it turns out that the symbolic aspects of the language actually underlie all other capabilities of the language. For instance, when you define a function in the Wolfram language, it is actually a pattern replacement, essentially. When you look at the full form, you get these sub-values that are essentially defined as pattern replacement rules. So pattern replacement rules, having the ability to pass the entire syntax tree, pattern match on the syntax tree, and then transform various components of the syntax tree, or the entire thing if you want, is quite unique. This is not done, basically, you cannot do this natively in pretty much any other language that I can think of. Perhaps, not Fortran, but Prolog is one of the languages that comes to mind where you can do this directly. Lisp to some degree, but really the Wolfram language is quite unique, and when you look at it, it is the fact that you can do symbolic manipulation on a large scale that gives the language its power. And I'm going to give you one example, but first I'll give you a historical sort of component here. When you look back in history, because the concept of numerical versus symbolic and so on affects pretty much every STEM branch, science, technology, mathematics. So in mathematics, in the history of calculus, for instance, you had these two sort of like competing approaches to it. Newton did a lot of the calculus because he was a physicist using essentially a numerical approach called quadratures. So when he was doing integration, he was essentially looking at geometric patterns and integrating these geometric patterns. Well, by pattern, they were actually essentially like squares and rectangles. And so we call that, the concept was called like quadratures. When you look back in history, there was a reason why that was essentially like a numerical approach. Leibniz, on the other hand, was he lived essentially at the same time as Newton in the 1600s, late 1600s, I believe. He developed, he was more of a philosopher, he wasn't really a physicist, and he developed like a symbolic approach to it. And both have a trade-off, and I'll give you an example of a trade-off when I get into this bubble sort here. But for instance, like when you look at differential calculus, the numerical approach is actually hard because you have noise, and it turns out that differentiating a signal is a high-pass filter. So it's actually hard and noisy. Whereas symbolically, oh, did I put this backwards here? Oh, I think I've got this completely reversed, actually. Sorry about that. I was in a hurry. But actually, this should be like hard and easy. I'll switch them on the next time around. Integration is wait a second. No, I'm sorry. Okay, these are correct. So the reason why differentiation is hard numerically is because you get a signal, and when you differentiate it, you are essentially highlighting the high frequencies, which is very noisy. Whereas symbolically, differentiation is easy because essentially you can use the chain rule. So using the chain rule, essentially you can differentiate pretty much any symbolic function. Whereas when you integrate things, I think everybody who's taking calculus, even at the level of high school, understands that when you integrate things, when you can use, like, for example, like Riemann integral or even like Lebesgue concepts, these are essentially numerical concepts, and you have limit theorems and so on. But these are very easy, like numerically. But of course, you cannot integrate most functions symbolically. It's very difficult. The fact that over the years and centuries, we've been able to create more methods that can integrate more and more functions is really a testament to the fact that this aspect of mathematics has been pushed, and that really underlies, for instance, Wolfram Alpha's step-by-step solution, problem solving in calculus. But generally speaking, that is very hard to integrate symbolically. So here's just a quote from Leibniz, who's basically saying, and this is very general, okay, it doesn't really apply just to mathematics, but it applies to all of science, I believe. He's saying that if we can find the suitable symbols, in other words, characters or signs that can express our thoughts, okay, he was a philosopher, so he was just talking about thoughts, as clearly as we can express arithmetic concepts, in other words, like numbers or geometry express lines, then we can essentially extend reasoning beyond what we can do with arithmetic and geometry. Now, he said this in 1677, so you can imagine mathematics was not very well developed, okay? But I think that the Wolfram language is a testament of what we can do in the 21st century, in the sense that you can manipulate databases or symbolic expressions in a similar way that you can manipulate numbers and geometry expresses lines. Okay, so in other words, you can think of most languages as just manipulating numbers, for instance, right? Of course, you can pass functions, right? But the way that the Wolfram language does it is quite unique, and it really is worth bearing that in mind, that you cannot find these kind of capabilities in most other languages. So here's an example that I found on Stack Exchange. Here's an example. This is just, I just copy-pasted this as a figure here, but here you have a bubble sort. And this bubble sort, of course, this is like a most basic sort of very slow procedure that you teach to undergrads or even high school students. How do you sort a series of numbers beyond what we can do with arithmetic and geometry? Now, he said this in 1677. The bubble sort is the easiest concept to teach. Here you have a one-liner that is essentially using pattern replacement rules to generate essentially the bubble sort. It is very slow, as the poster points out. This is n cubed. Typically, a bubble sort is actually n squared. And the reason is because the way that this replacement rule step-by-step is actually worked out, as you can see. But the good aspect of this is a one-liner. How it works is basically saying, look at any sequence, and if any two elements of the sequence are out of order, meaning that if x is greater than y here, if x is actually greater than y, flip them. And this is what the flipping does, right? And these triple underscores on the before and after, before the X and after the Y, means that you can have 0 or more, in other words, like numbers or geometry components of the sequence there. So if you can imagine a list of things, then you might have nothing before the X, or you might have nothing after the Y. So this is actually, the way that the matching rule has to be done. This actually goes through this list many more times than you really need to. So it actually represents the bubble sort algorithm. A real bubble sort algorithm, would be able to do this in ON squared. But think about how much easier it is to understand this one-liner compared to the procedural version of this, where you explicitly step through each item in the list. This is how the bubble sort would work if you did this in pretty much every language. This is done in the Wolfram language, but you would do this exactly the same thing in Python or C or C++ or anything like that. This would be exactly the same, where you manipulate each individual list. So now this is like 5 lines, and it would be kind of tedious to go through and explain to people. But this has such a nicer, more human readable component to it that is basically saying, here's the rule. The rule is, if you see any 2 components that are out of order, flip them. Manipulate, and that's basically what bubble sort does. And then, of course, it leaves it up. You have to iterate this over and over and over again until you understand that this is actually going through this list many, many times. So for a list of like 100 different numbers or digits, databases, this bubble sort would actually go through tens of thousands of times until you run out of like iterations at some point. But so okay, so what you want to emphasize out of this is that there is a trade-off, of course, in speed. But can one push, and maybe this should be a homework problem, can one push this abstract rule pattern matching and transformation so that to make this like ON squared rather than ON cubed, for instance? And if anybody wants to, I started writing some notebooks. I'm not going to share them today, but basically these notebooks take some real-world examples of how this works. You get exactly the same answer with this or this, right? But to me, the point is this is much more readable. And as you get into more sophisticated algorithms, this is much more of it's a boon to be able to have this level of abstraction that, again, it would be very difficult to do in other languages. Okay, so that concludes the part of the symbolic. I'm sure we'll come back to it at some point because to emphasize the power of the language. And anytime you do replacement rules, like I said, like you're basically invoking or using the symbolic aspect of the Wolfram language. All right, so step 2, I think I might defer this actually, but if we come back in time, I think this is going to be a regular feature of future sessions. We're basically going to be taking some 1 or 2 or 3 functions from my notebooks. And by notebook, what I mean is essentially, here, let's just go to the notebook here. These are what I'm calling, this notebook is an appendix in my book. And I believe that introduces before, so I'm just going to scroll through this very quickly. These are all functions that I created in a span of about 5 years or so when I worked at the Veterans Administration. They were for certain projects, but then I realized that these are very generic, and these could help you in any project that you do that are associated with data. And in fact, many of these really could be in the language itself. We're talking about things like key group by, and there are many things that are essentially very, very low level sort of functions. And they're very nice because they're one-liners. Maybe I'll talk about this one later in the sessions if we have time. But I would definitely like to break this apart. And I think I want to stress that you can be very creative with this language. It's kind of fun to come up with these one-liner functions. And I'm currently in my job, I have to write in Python. And to develop in Python, I'm trying to replicate a very tiny fraction of the query capabilities of the Wolfram language in Python. And it's very difficult to do. I mean, you cannot do this stuff in a one-liner at all. You have to create everything is just much more involved to get anything done. I mean, even basic mapping, all these kind of functional sort of thing. So I think that I would definitely like to get out. I hope that there's interest in me showing off these functions, because it's fun to come up with these things. Basically, you notice a pattern in your data work, and you say, you know what, I can reuse this. I can reuse this in other projects. So the language basically enables you to be very productive, essentially, because you can reuse these components that are easy. When something is one-liner, it's very easy to take it and improve it, right? And it's very easy to refactor if needed. If something like, as you see in Python, this might be several lines or more, it's much more challenging to refactor, to maintain, and so forth. So I think we'll definitely try to set up some time in every future session to do this, to show off some of these functions. So I hope to have some time to get back to it. Okay, so the third part of the session is to finish up our FICO XML notebook. So if you remember, and this is, I'm not going to get into the entire thing, of course, because we have the previous 2 sessions where about this. So we started this and went through it little by little, and we did the data prep part of it. And I think that we can spend a good like 20 minutes or so on finishing this up. And from now on, it's essentially data analysis. But before we get into the data analysis, there's one thing that I wanted to do that I improved. There was a function that got us in trouble. When I started doing this in a live coding component, I had a function, and it gave us some trouble, and it basically got the spinning wheel. And I thought to myself, and this is the function here, and I thought, can I take this function and refactor it? Because it's a bit of a pain in the ass. I don't like creating separate functions. Again, like in Python, you sort of have to do this all the time. You have to create these external functions that then you call when you actually do the data work. Whereas in the Wolfram language, you use patterns rather than functions. You tend to basically write out the query, and you're building it as you go along. But somehow I had to use this function, and I didn't like it. And I thought, can I actually get rid of this function? Can I come up with something that does this without using that external function? So if you remember, let's start with this. So the empirical CDF function contains the following types of code here, or the following data. These are all internal empirical distributions. And just to give you a little bit of background, if you don't remember, or if you have not seen the first couple of sessions, the challenge here is to take some good accounts, bad accounts, and then there's actually both combined. And there are 24 predictors, and there are something like 10,000 data points. And the issue is these predictors tell you whether the account holders, meaning somebody who applies for a loan, should actually get the loan. And the job of the machine learning classification, or even regression if you want, is to say, should we give this person the loan or not, based on their numerical patterns compared to every other account. And the accounts are grouped into good accounts, meaning they're the ones that actually did pay back the loans, versus the bad accounts who did not pay back the loans. And they're very close to one another, okay? So these figures were generated from the underlying data distributions. The data distributions are just sets of points. And in the last coding sessions, we showed how you actually go from one and you get this staircase sort of distribution. Well, what I had to do here was to create an association map. And the association map, essentially, just to give you one of them, let's just go under the both branch and then go under ERE. ERE, I think, is like external risk. So it's just one particular distribution that they have. And in here, if I can evaluate this function, right? So if the functions are normalized, they go from 0 to 1. So if I type in 0, it should get a value very close to 0. If I type 1, because they're normalized, you get values that are very high, okay? But any other value would essentially work. So how I created these figures was essentially by sampling them. And I have a sampling width, and I wanted to get away from that. Basically, I just wanted to get away of this entire sampling thing. So here I'm using a list plot, but then essentially I redid it using plot internally. So let's see if I still have it here. I hope I plopped it in. Okay, here's the new version using plot. And again, it starts off with empirical CDF. So let's just go through it. Let's just do the live coding part of this. So when you have the, so let's see here. So you can see that they're pretty much the same plots. What is the difference? The difference is I did not sample them. I used plot. And how does plot work? Well, plot starts off by using a function. So you have to transmute these so rather than sampling and rather than taking 0.4, we're just going to create like a function of this. The way that we create a function is actually here. I'm going to take this, I'm going to convert it to a function of x. And I believe that this is how you do it. Let's see if this works here. If I create this, do I create a function? Yes, okay, so this created a function of x. And these bools essentially are step functions, right? So the Boolean function essentially gives you a set of, they're essentially a set of step functions that are not dictated by myself. They're not dictated by even sampling. Rather, they're dictated by the empirical distribution themselves. So if you look at where these Boolean step points are, they're dictated by the data itself, right? So it's whatever, if there are 10,000 data points in here, however the distribution is, this is how the distribution tells you what these breakpoints are. So it's much more natural in a sense, even though they're so fine that it looks as if they're spread out. When you look at this one, like MDP12, which is another predictor, you can see that the step points here are much wider than they are here, right? So there's no step points between here and here. Let's just try it. We should get many fewer So if I do MDP12, which is another predictor here, I should get fewer bools. So you can see that there are very fewer step points. And again, these were not dictated by the user. This is dictated by the data itself, okay? So once you have this function here, what we're doing essentially is using a function, which is one of my functions called KeyValue Replace, and we're using plot to plot all these. Now, everything else here are basically just, let's see here, up to here, they're essentially, yeah, these are all options to plot. Okay, so let's just go through it a little bit at a time. So when I take this, let me explain why I need to transpose this. So if you recall, forgot the H. So we're starting off with all the data, and these are the empirical, again, cumulative function distribution, which is a aspect of statistics. The reason for transposing, what's going to happen is now the 24 predictors, ERE, MOTO, et cetera, they're going to go to the first component, and the both bad and good are going to go to the second component. The reason is we want all three of these. We want plot to essentially handle all three, basically the good, which is the blue, the red ones, which is the bad accounts, and then the cumulative, which is both of them, which is the gray. And so this is as simple as doing that. Okay, so now with the transpose it, now for each one of these 24 predictors, now we have access and we can do a key value replace on both bad and good, right? We're essentially going to be doing the same thing to both bad and good branches. All right, so let's see if we can do this. So if we have key value replace, now I'm going to pass this function. I'm going to create this function here. So do this. So basically now, let's see here. If we have all, so that means for all goes under, for all of the predictors, then I'm going to query. And the reason for the query is because I have some subsequent things in plot. For all of the predictors and all the branches, and now this all is going through all the both bad and good, so there's three branches there. I'm going to apply this function, and I'm going to create a function of x, just like I showed earlier. Okay. So you're going to see a lot of these bools essentially in there. Okay, so each one now has bools, and we can verify that the both is just one branch, but there should be three columns here. If I scroll to the right, you can see there's 24 rows, each one for each predictor. So let's see here. Yep. So this is the good branch. So again, I'm not going to go through all this stuff in detail, but essentially I've transposed these and created a function for each one of these. So now we're ready to plot them essentially. So okay, so we're gonna use one of the functions, and so okay, so this would be one example of how we can use key value replace. Value replace. So let me just show you what this function looks like. And again, this is is going to be bundled in my book. Key value replace. Okay, you can see that it's a very simple function. This is this is even below a one-liner, right? It's very simple. It just uses key value map with a list, and then it replaces, and we're going to give you the rules. Okay, so this is how it works. So basically, now this is. So let's see, where is this happening here? So key value replace, this is happening at the second level. So it's going to replace, I'm going to take the keys, which are the both good and bad, which are called the risk class. Okay, so risk class. And then the data itself are going to be the bool functions. And now I'm going to plot it essentially. And now I'm not going to use all the different fancy options on it, but this is basically just to show you that now just essentially, you're picking off the data portion of it. And the X, which we introduced earlier over here, now that's ready to be used because that's necessary for plot to essentially, show the limits on the X-axis. So let's see what happens here. This might take a little bit of time, but I think it's worth it. So again, let me give you like a little play-by-play here. So again, like we're going to do some post-processing after we do this, but essentially this boils down to doing this. Okay, so it's very simple. Basically, if you know where to apply this function, and then you combine both the keys and the values. Again, the keys and the values are necessary because you want to create the risk class. So why did I pick off the risk class? because there's a dictionary that essentially has the red, blue, and green, right? So this particular dictionary, which is an association here, literally takes the strings both good and bad, and then is going to map them to color. And I use that here in plot style. So plot style essentially is going to be applied to risk class. So let's see what happens here. Oops. Okay, so here's one of the unfortunate things of data set is doesn't necessarily understand graphics, but I think we can just do this. Let's say 207. Let's just normalize it. Okay, now you can see where this is coming from, right? So now for each one of these, this is before I'm actually using plot style. So and it's before I actually use show. I combine them all with show. So plot is actually creating a separate plot for each one of these. So for example, for ERE, this would be, let's say, I'm guessing this is going to be the red one, this is the gray one, and this is the blue one, right? So now I've picked off the keys, but of course I symbolically, they're there under the risk class component, okay? But essentially this is what's happening. Under the hood, you have these 3 plots per. And then let's see if we combine them. Let's just do this. Plot data. So let's see, plot style. Let's just do the plot style here. Plot style. And then I'm just going to copy paste this here. Actually, let me just show you what the data dictionary looks like here for risk colors. And again, it's just a simple association, okay? The associations are usable in all sorts of different contexts. Well, it's actually a data set, but normal, under the hood. So by the way, reuse this and use these for labels in publications. I mean, they're ready to go. You don't even have to do anything after the fact, So once we have this, so the plot style now can use this. So let's just do this, put this in here, and then evaluate these on risk class. Okay, and then let's just normalize this. Let me just do, rather than all of them, let me just do like a few. 1, 2, 5. So normalize them. Hopefully you will see at least that they're colored. And then apply show, essentially, I think puts them all together into one plot. I think so. I'm doing the first 5 here. Yep. Okay. So you can see how this is valuable, and this is, again, now this is a very simple way of picking out. Given our discussion earlier about symbolics, here you're just picking out something essentially in a list of 2 things. So it's very simple, right? But you can actually go much deeper. You can, if you had multiple components of the keys, if the keys were themselves lists or something like that, you would be able to pick out like different parts of that if you wanted to, because that's essentially the language allows you to pick out. And again, you think of it as being given the entire syntax tree that you can operate on, pattern match on, and transpose or do transformation rules on various components of that. Okay, all right, so that's about it. I'm not going to go through the show. The show essentially puts them all together. Yeah.
Somebody has a question, since you mentioned the comparison between Wolfram language and other languages.
Sure.
Will your notebook show any comparison demonstrating how much easier it is to do the certain task in Wolfram language versus other languages?
Not today. We're planning on doing this. We started an online spreadsheet, actually, that shows you, they're not necessarily...
They're asking about your book.
No, the book actually does not get into that, but I think just because we want to get it out of the way. But in the future, I think that's something that we definitely want to do. I think it's worth because it's not just like a 10% improvement. It's like 10-to-1 ratio almost, 5-to-1 to 10-to-1 ratio, which pretty much translates into time. I really feel that the work that I did, for instance, in my current work, we spent months and months doing data prep and data cleaning. I think it would have been done a lot sooner, like within 1 month, I would have been able to do. And in fact, I had to do certain things in the Wolfram language, and I'll be happy to share some of those things because we had de-identified the proprietary data to do that. So for some things, Python is just too involved. The packages are not there to do the fancy, for example, like hierarchical data. Pandas doesn't do that. So we kind of have to roll around to do this kind of stuff. So yeah. Yeah, okay. So now at this point, let me break here just for a second. I wanted to show people something that I meant to do this at the very beginning. But since we have, you notice that the language here we just have, you notice that this is a list of graphics, okay? And I think everybody understands this is, in fact, a list of graphics that has in fact, this is actually, let's see, this is a key value map of overscript. So this is actually being overscripting the graphic above a string, and then the entire thing is actually an array, right? This is actually a list of things. But did you know that you can actually do this very nicely with nested association? This kind of gets back to something that would be really, really difficult to do in Python or anything like that. This is something that I'll be happy to get more into this in a future session. This is a project that I did at the Veterans Administration, where we took essentially data, chronological data for patient charts, and we essentially mapped a bunch of graphics. And then look at this. This is group bys. Using group bys on the timestamps gives you, for instance, Friday the 1st of July, and then this is another level, and then you can further group by. So this is several levels of group bys that gives you these, on the timestamps themselves. Okay, so you start off with timestamps, and then you just keep taking just the, the year, the month, and the thing. Look at these arrows. These arrows are actually rules in the language. Okay, so these are actually components of rules and associations. All we did is essentially put frames around them, or put graphics around them, or highlight them in various ways. But this is essentially a very easy step to go from the underlying data set, take a couple of group bys, and essentially do this sort of like highlighting. And we wanted to create like an actual fancy kind of scrollable patient chart, a chronological patient chart, which we call the I think it was called the clinical event browser, essentially, right? So these are all the events that are like in the patient record. And just by doing these very simple things and then doing this kind of, so I think these are rules and just kind of nested associations. And yet, look how different they are. They essentially are ready to go. I mean, if we can put these on the cloud, I'm really confident, and put kind of interactive things on them, you almost have an actual minimal viable product that you can put out there. And the doctors like that a lot. They requested sort of features and so on. But man, it took us more time to actually clean this data because they were in various formats than to create this particular mockup of doing that. And I think that, like I said, like, use your imagination. You can do so much with this language that if you try to do this in Python, and first of all, you cannot do like keys in Python, for instance. They have to be what are called like hashable. So there's only certain data structures that can be hashed. Like, for example, tuples can be hashed, but not lists and not dictionaries themselves. So you're really, really, up a creek when you try to do these fancy things like putting, these kind of fancy things. Like if we can turn this into buttons, the Wolfram language, because it's symbolic, I come back to this point again and again, because it's symbolic. If people want to collaborate on future projects along these lines, where we take some of this is a key, right? This is the value of the key. This is the key. If you could turn this into a button, for instance, and cloud deploy it, now all of a sudden you have something that you can kind of manipulate and feed to database queries and so on. But again, like, I think it would be so difficult to do directly with Python that you have to create completely separate like languages and packages to do this sort of stuff. So this was part of a 6-month project that I did at Veterans Administration for chronological visualization, and I'd be happy to get into this either offline or in a future session. Okay, but again, combining the multimedia readiness of the language is really incredible. Okay, so back to this. Let's just finish up this FICO XML challenge here. There were some latent questions from last week. Now, I might not have time to do a lot of live coding here, but one of the questions that I remember, and I think maybe Mads asked, was how do you rank order the importance of the predictors, right? So we have these 24 predictors. How do you know which ones are important and which ones are not? Okay, so I did it in a couple of ways. Here's one way. One way is to basically look at the difference, essentially looking at the statistical properties. You essentially look at how far apart are the good versus the bad accounts, right? So how far away, not just the peaks, but essentially you're looking at the cumulative distribution. So the further apart two peaks are, that basically tells you that it's a predictive power of the predictor to say, yes, if given any particular value, I'm much more likely to tell you that if you get a 0.5 here, that you're likely to be a bad account rather than a good account, which is the blue one, right? Red is bad accounts. You can see that if somehow you have an ERE score, normalized ERE score of 0.5, what that basically means is like a lot more of the bad accounts have a value of 0.5 than good accounts. Yes, there are some good accounts that have a value of 0.5, but more of them have a value that is higher up, like around 0.8. That's where the peak is. So this particular predictor has a very wide gap between the good and bad classes, and therefore it's a pretty high predictor. So if you do this, and again, I did this computationally here, essentially by sampling, and I don't think it's worth getting into this, but you can see that there are some kind of nice steps here where you can use transpose at multiple places to essentially push the keys back and forth. But basically, the discriminant power is essentially just taking the good minus bad, totaling them up, and getting this tally fraction. So let's see let's see here. Actually, let me just show you one step here. And then you get a rank order list of these. Let's see if I can show you this. Okay, all right, so now essentially you're sampling, right? And probably you can get away with using those Boolean functions if needed, but here I just simply did a transpose. So let me just do that, transpose. Remember what transpose does is just taking the keys at level 1, transposing with this one, but then you take the keys at level 2 and transposing them with level 3. Okay, so let's see what this looks like. Okay. All right, so now you have, for each one of the sample layers, you've pushed the good and bad and good into each one of these. So let me just pick off like the ERE, for instance. ERE and normalize it. Just to show you what that looks like. Okay, so now they're keyed in, and now you have these particular values here. Okay, so now, let's just go back and might as well finish it up here. Now I'm gonna total them and take these and divide by 100 here. I'm just essentially saying, what is the difference between them? That's all I'm doing is essentially for each one of the sample values, you're essentially computing this component, okay? And then totaling them up across these. So let's see what this looks like. Let's see this extra bracket. Okay, so now for each one of these predictors, essentially, you get a total of the differences for each one of the samples across the domain, which is normalized from 0 to 1, okay? And then after that, of course, you just, tally fraction just gives you both the tally and the fraction. You reverse sort it, and once you have it, you essentially plot it. So this tells you what is intuitive. The ERE component or the predictor is very high. In other words, this is the most trustworthy component to be able to tell the difference. If you were just to look at one predictor, you might as well look at ERE, because that's the one that tells you. And of course, just like everything in real life, there's like smooth continuum, essentially. There's a power law probably across these. But if you were to look at some of these, you can essentially threshold and just say, you know what, let's just look at the top 10 of these predictors and ignore the other ones because they're so small. If you look at a predictor down like NTO 12 or something like that, there's not a lot of difference. There's just simply not a lot of difference. So look at NTT, right? If an account comes along has got an NTT value of like, let's say 0.2, how do you know that they're a good account or a bad account? These curves are so close to one another that the predictive value is very small because of that. Okay, so this is one way in which in data science, after you do all this normalization and prep work, you get these nice ways to be able to discriminate and essentially, I believe this is called predictive power, essentially. Okay, now you can also do correlations among them. So let's see what I did here. I want to show people this. We probably don't have a lot of live coding to do because some of these steps are pretty involved, essentially. But you can kind of also do dimensionality reduction by saying which one of these components were correlated with other ones. Let me just get to the bottom here because I want to show you a different way of doing it. So this is really the payoff for the project here, was to be able to predict for each one of these components, essentially build a classifier per, okay? And the value added of the language is that you can scale up very nicely across these different components here. Let me just skip most of this. So feature selection, prediction here. So what I did is essentially say, you can kind of create the top 5 based on the earlier rank ordering. You can just say, I want to do a classifier based on just the 5 or the top 10 or the top 15 and so on, right? And again, the language lets you essentially do all of these at the same time because you can use all, right? You can see how many times in the projects I use all. The more alls you use, the more power you have because it's the opposite of using selects. If you do alls, you're essentially doing all these group bys and you're doing all the branches in parallel, essentially. Not in a computational sense, you're still serial, but in terms of the user interface or the programmer interface, you're doing, for example, you get all of these at the same time, right? So you can just do these things like very, very nicely at a very high level. Okay, so let me just cut to the chase here. The classification accuracy is another way of doing it to get the prediction value. So what it created is essentially, so again, it's unfortunate that I won't be able to get into the much live coding here, but I think I had to create a function, and again, maybe for homework, if you can, just like I did for the graphics earlier, if we can avoid these functions, we should be able to apply this query directly into here somehow, but I wasn't able to do that because I had to sort of like pass some arguments into here. So the good and bad ROCs, essentially, this function, it's a query that basically has to go through and compute the area under the curve. And before you can compute the area under the curve, of course, you have to create and just say, essentially, how many false positives and how many true positives do you get as you sweep across and you say, my threshold for saying that a good account versus bad account is X. X goes from 0 to 1, and it's somewhere. And as you sweep across it, you essentially get these values of the predictive accuracy, which is like the true positives and the false positives. Because that's all in the data, right? The data gives you, we know they're labeled, right? So this is essentially, this is labeled data that has the classes given to you. So we can give you the actual true positives and compare them to what the predictive accuracies are by essentially like sweeping this threshold. So once we have these, essentially you can create the area under the curve. So you can read these off. So the area under the curve for the ERE is very high, is like 0.6. So something like 77% accuracy it would be if you follow this curve as you sweep across it, right? The area in the curve is basically the dotted red dots, which are the actual samples. So it's actually like a piecewise linear versus what you would do by basically throwing dice, random evaluation. Because the data, be careful when you do this. In this case, the good and bad accounts are balanced. In other words, you have about 5,000 of each. But in cases where they're unbalanced, you have to be careful about interpreting these as the random throw because you'd have to do something other than uniform sampling. But once you have these, and again, I think that I want to finish this notebook. It's going to be in the book no matter what, so I'm going to explain it much better in the book. But basically, once you have this, you're in a position to essentially compare the classification accuracy of each one of the predictors. And this is what they look like here. Okay, so you're just reading off these AUCs. The AUCs is the standard metric for saying the area under the curve. And it's not a coincidence that the ERE is number 1. And then as you go down, you can see that they get closer and closer to just like basically being random. In other words, you would not be using this NITD, at least by themselves, you would not be using these. Okay, you can combine them in some ways, but by themselves, they're not that useful. And the idea about this XML, meaning the explainable machine learning, is that I wanted to get away from using combining things as in a linear algebra sense and just saying individually, what does each predictor say about each particular account? Okay, so essentially each of these predictors gets to vote on whether the account should be or should not be considered a good or bad prediction. Okay, now one thing. So to answer Matt's question from from coding session number 2, so the AUC is the ROC accuracy. How does that compare to the predictor discriminant power that I discussed above? So here's one way to show these, and I show this by basically taking the Spearman rho, which is a robust correlation between the two. So what you see here is a scatter plot for each one of the predictors. You essentially show both the discriminant power along the x-axis and the risk classification based on the area under the curve. Now you can use one or you can use the other, and this plot essentially tells you, do you trust one or the other? Well, in general, you can see that these sort of like increase, and the Spearman rho is about 6.2, which is, it's high, but it's not very high, actually. What this tells you is that for some predictors like ERE, they're very high in both, right? Both the CDF, meaning the statistical discriminant power, is very high. That's based on the raw data, and also the risk classification accuracy based on the threshold classifier is also very high at about 77%, let's say, accuracy. So that means like you can pretty much like trust this ERE. Then you would also be trusting things that are essentially on the upper quarter here. You would probably not want to trust this MR17. What this tells you is that it's in the middle of the pack in terms of discriminant power, but it's actually very low in terms of a risk classification AUC. Some of the underlying reasons include, for instance, if these are highly quantized, meaning they have very few values, then it's very difficult to actually compute statistically because they just fall into like, let's say, like nine levels, 9 values that they can have. So in this particular one, you might trust its discriminant power, but its classification accuracy is very poor. You would probably want to filter this one out. Okay, so this particular graph tells you that yes, overall they're both sort of, you might as well, if you want to, you can just use the initial CDF discriminant power and not build any classifier, or you can kind of compare the two and just sort of say, well, I can weigh now if ERE says that you should be on account and get the loan, I will probably trust it. And if maybe like these particular, let's say 5 or 6, say that you should be like you should get the loan, you might want to trust it. But probably if this one, if ERE says you should be a bad account, but the NTT says you should be a good account, maybe you shouldn't trust this as much, right? So you can weigh, you can use this as a means of weighing. Okay, so basically, yeah. So I think that pretty much like concludes here. So let's build the actual like reason codes here. The reason codes. Let's see here. Okay, so essentially what this means is that we have for each one of these top 10, top 20 codes, and actually I forget which one I used. If did I use the top 10, top 5, and so on? Which one was it based on? Was it based on, oh yeah, okay, it was based on CDF, discriminant power. Okay, but you can base it on either one. You can use it based on either discriminant power or the AUC, right? Now what this does is essentially, this is the end product. This is something that you would put in front of the client, right? In front of the bankers or in front of the regulators, that says, okay, here's account 001. And account 001 says that ERE tells you that this account, based on the underlying value of the account, and remember, like each one of these accounts has an individual value. These are all normalized, of course. We spend a lot of times normalizing them, okay? Some of them are missing, of course, right? But this is the actual value. This is what your data says. Based on this data, you have to make the classification. Should this account get the loan or not? And what this reason code report says is that, okay, let's let all these codes vote individually on whether you should get whether account 001 should be considered a good account or a bad account. Now, in this particular case, we know we didn't separate these out into training set or test sets. This is something that you will do in a real world challenge or in a real world, let's say in the real world context. For this particular challenge, they gave us about 3 months, so I didn't even do this. This is what's called an all-in approach, meaning that you take all the data that is given to you and you create a method. You don't separate them into holdout set and training data and test data. But if you did that, then basically you would sort of separate them and take out the labels for a portion of these, and then test whether the method itself is good or not. Okay, so this is an all-in approach that basically says, okay, now we've created a method that does the classification. Now, essentially, you can create an overall accuracy based on this by essentially saying, we know what each individual predictor tells you, and now let's just say, how many of these things, how many of these predictors will say that you're a good account versus a bad account, and then you can do the statistics, the overall. But essentially, based on this, the reason code report would look like this, right? You have an account, 001, and then it tells you that 13 predictors would classify you as a bad account, and 10 of them would classify you as a good account. So you can see it's very, it's very dodgy here. It's not as if all 24 would say you're a good account or not. And of course, they mix and match too, right? But basically, this reason code would be something that would be very easy to interpret, because you would essentially just say, okay, I understand how these are not mixed combined, right? This is a vote for each one of these predictors that is saying something about the account. Okay, so this would be the end result, or like sort of like an end chart. If somebody comes along, they have a bunch of these numbers as inputs, they get normalized, and then you spit out this and say, well, you know what? We're not going to give you the loan because, look at this account, 004. There are 19 codes that basically predict that you're going to be a bad account, and only 5 of them predict that you're going to be a good account. Okay, so that essentially concludes this. We have about 10 minutes left. So yeah, so let's just like open up to questions.
So let's see for users if they have any question. So far, no question.
Okay, if there are no questions, I think I can take 1 minute to describe 2 functions.
Oh, please go ahead. Yeah, the list of your functions, that would be very helpful for our users.
Yeah. So let's just do that. Let's see, someone as well go in. Let's see if I have this. So KeyValue Map. So if I go to, I believe I just put this on Stack Exchange actually, so we might as well go there. Mathematics Stack Exchange. And let's see if I do this upper level. Let me just do this keys. Database query for keys of upper level. So this person wanted to know if you have a data set well, it doesn't have to be a data set, by the way, okay? So most people focus on data set, but it's actually, you're working on the associations. So what you want to do is combine keys and values without destroying the association structure. And that's what the desired output is. So you can see that the key becomes part, it goes into the values. So there's a couple of people that have replied, and I think that these are, good. I think I should upvote these. They're good answers. WReach, of course, is a major player in this area here. But yeah, you can use map index, for instance, to do it. Okay. Now I've done these. Now if you notice map index, if you replace this and you give it a function that you want to pass into it, you would essentially get what I call the key value maps. In the key value maps, you take an association. So for instance, if I do key value map and then I pass list and reverse, then you get this. Okay, so in other words, actually, let's just do this directly. If I have this as input, let me just take the entire thing. Now let's just go here. Okay, so if I do key value map, and now I'm gonna pass a generic function. So let's see here. Oh, sorry. Like I have multiple nodes with this. If I do this, I'm passing this. I'm not going to normalize this. Okay. You can see that I'm passing a function f, and this could be an arbitrary function. Okay. If I can also do this to the keys if I want to. So I'm basically multiplexing them. I can just say f, and then leave the values alone. So you can see that you're mixing and matching and putting them up in the key part of but you can still, unlike the built-in key value map, which is the uppercase version key value map, that would destroy the association. It would just give you essentially, this part of it. So this essentially just preserves this. But in addition, it allows you essentially to pass two functions and do essentially like a matrix. So I can pass, oops, let's just do this. If I do F and G, you can see that I've passed and I've merged both the keys and values and the keys and values under G here. So now if I do, for instance, list, you get back what the original poster wanted. So I just turn them into list. And then of course you manipulate it by reverse. Because in his example, A comes second, right? Okay, now based on this, now I have a function called key subkey map, because, and look at the definition of this function. It uses key value map, and this is the definition here. Now, I use this all the time, actually, and in my book, I use this a lot, and I'll give you an example of why it's interesting here. Let's see, where's my thing here? Okay, so key value map, and then I use, okay, so suppose you take this example and make it a little bit more complicated. You have this data set that has association as values. Okay, so this is an example of a nested association, right? Okay, so you have keys, and then you have the subkeys, which are like, for instance, 2 is a subkey, Y is a subkey, Z is a subkey, 2 is a subkey of C, and so on. Okay, now I can use this key subkey map, which is defined here, and essentially uses the previously defined key value map with a little bit of replacement rule. And again, keep in mind the symbolic aspect of this. We're using replacement rules. You can get much fancier if you want to here. Here it just uses literally just, here's the key, and here's the association that is the lower level association. And then we just use a key map and query. And what happens is you get this out. Okay, now you have key subkey map. Now, why is this useful? This is useful because in my book, you have a bunch of files that essentially are, let's say that the unit of analysis were like, in our case, were the visits, the encounters between patients and doctors. And each visit had a slate, and you have to do temporal synchronization. Every one of the visits, that would be like A, B, and C. These were visits that then you would look up in a dictionary where the slate synchronization point is. And then you have to pass it underneath, because then you have a bunch of timestamps that you have to subtract from the slate. So the slate time point then, for example, here, you can see that the F goes into, suppose that Y and Z were timestamps. Okay, now what you're basically saying is, I want to look at visit B. You would look up in the dictionary what the visit B slate point is. Slate point is essentially just a temporal, it's a timestamp that tells you, here's when the visit starts, right? So we have all these video signals and eye tracking signals and Kinect camera and all these things. Basically, you have to, every visit is different, and you have to look it up. So basically, this key subkey value map, key subkey map, essentially, you would put in minus here. You would say like minus, and I'm not going to do it here because you can't subtract y from 11, but if these were timestamps and the v you would look up in the dictionary, essentially you would perform this automatically. So this entire association would essentially be a time signal keyed in by the timestamps. And so this would allow you to do this very, very easily for all the different visits at the same time, just by a lookup, essentially. So this is the value. So this is something that I use all the time. And if you pick up on these tricks, and again, you have to, number one, notice that there's a pattern that you use over and over. In this case, the fact that you wanted to have something up here that gets into, again, this is not really visible for this minimal example, but in my book, and I hope that in the future, we should actually base some of these coding sessions on chapters in my book, you will see this distinctly, how this comes into play. So step one is you have to notice a pattern. Two, you have to come up with a function that sort of like encodes that. And three, hopefully it's a pretty easy, simple function that is like a one-liner. This is very simple to code up. Once you understand these kinds of things, you will see these kinds of patterns over and over again. So once it's coded, then you can reuse it. You can reuse this for multiple projects down the line. So yeah, so this is about it. So I'm glad we got at least a couple of functions in. And if you care to read more about it, obviously you can. I will prep a notebook that has some of these answers, and you can also use some of these resources that we can link together. Okay, so I think that pretty much ends it here.
Excellent. I guess, this is a very good point to wrap up today's session. It was the third live streaming session with Dr. Alan Calvitti, who discussed about data science using Wolfram language. You can follow us on Wolfram YouTube channel. You can also reach out to Alan directly through Wolfram community. Thanks, Alan. Thanks, everyone, for watching. Have a good one.
Thank you, everybody, for participating. Thank you, Matt.